Well, thanks a lot, Pablo.
Well done. Well done.
You're
Thank
welcome.
you very much. So we proceed in our schedule, and our next speaker is Cornelius, and he will be talking about a simulator that we found somewhere by Swedish guys, but Cornelius will introduce this. And we did some common work, and he will give a sneak preview of what the NC4000 Novik simulator looks like. So, Cornelius.
Party time. Yes, we go from high-end graphics to no graphics at all. So if you ever wanted a paradigm shift without a clutch, here it is. Let's take a look at the simulator. Screen sharing. Would you please share? Here we share.
Yeah, well,
okay.
Black screen with green prompt.
Indeed. Hey, the 80s called. They want their terminal colors back. Is this readable for everybody?
Good for me.
Okay.
Yes.
Cool. Good. Novik simulator.
Too small. Small.
Say again?
Too small.
Too small. Okay, we can fix this. Just give me a moment. Change settings. Appearance. Change 18. Let's see what that does. How's this?
Good. Good. Now good.
Perfect. Okay. We'll go with this. Good. Yeah, Novik simulator was written in the late 90s at Chalmers University in Sweden. It's part of a thesis about an MP3 decoder in FPGA. The FPGA was implemented a Novik CPU, which at that point in time had been out of production for a decade. So to get an idea how the code was supposed to work, to write code, to debug code, they came up with a simulator. The simulator is mainly written in C++, fairly compact, consists of a couple module, the core itself, implemented as NC4K, then the environment simulation, which basically handles I/O, has a couple of general, this thing in general is just minimal memory management. And then we have the bench, aptly named. That's the main program, which offers, well, which brings up the whole thing, gets it going, allocates memory, and offers you a very, very basic, well, today we would call that hypervisor, something that controls a guest CPU, allows certain interaction with this guest CPU. The code itself compiles just fine on 32-bit Linux. As I found out last night, when you go to something newer, 64-bit, there are a couple of warnings, and there are some adaptations that you have to do to some of the built-in types of this thing because they've been used elsewhere. The code itself, the baseline code, dates back to the late 90s. It was written in Borland C++, which I'm pretty sure itself is long dead. There is a successor company, Embarcadero or something like that, where you can still get licenses for that stuff, but it's Windows only, so why would we be interested? Building this is quite simple. There's a make file for this. You're gonna make all the platform we are running this on is a Pi 2B. So 4 CPUs at 900 megahertz a pop, which means once we start that thing, it won't quite die. If we want to start this, we just invoke this, NC4K. It throws out a ton of text. What this thing now does is it loads from disk the firmware. The firmware used to, on the real thing, the firmware sits in 2 EPROMs, which are copied to RAM at part of startup. Well, we don't have a board, so the firmware is loaded from disk, from images that I retrieved from the original ROMs, EPROMs twice. Very first thing I did, because EPROM's life expectancy is not exactly in the 35-year range. When we come up, we end up in the hypervisor, which means we have a couple of very, very basic commands. We can display memory, and since Forth has 3 different address spaces, and these 3 different address spaces, return stack, data stack, and main memory, are distinct on the CPU. There are 3 different commands to manipulate or look at these. We can take a look at the CPU registers, which, since this thing hasn't done anything, are very, very empty. Of interest here is the program counter. An NC4K starts out when booted at address 1000 hex. So 4096 hex. Rest is empty. Pointers are reset. You can, since this is a simulator, due to the nature, the way this is coded, you can run this thing single-stepped, which with the original board you couldn't exactly do unless you were into really hefty hardware modification. Hardware modification, in our case, is not an option because there are only 2 known boards in existence, so we shall not mess with it. At some later point in time, I'm thinking about putting this on a microcontroller and see where we go with this. Anyway, we can run this thing. We say go, and it waits for a moment. And since this copyright notice doesn't look completely English, that's a hint right there that we are running with the German version of the firmware. We can do a words. Oh, lovely. Caps lock, please. You can do a words, and it spits this out. Now, if you got the impression that output speed was kind of not so fast, then you're not exactly mistaken. There are 2 versions of this emulator. Ulrich's does I/O way faster than this, because his version intercepts calls to emit and key, so the routines which display 1 character and which receive from the quote serial port unquote 1 character. His emulator intercepts calls to these 2 functions and switches immediately to native, to to what this basically takes the character that's supposed to be sent and shoves it immediately into the appropriate file descriptor. Mine doesn't do that. The Novix CPU, BitBingo's a serial port with software timing. My version, BitBingo's a no longer existent serial port with all the timing, and therefore this BitBingo takes longer. What else does this thing have? There is, since this is an emulator, there is a little bit of a timing penalty, but it does the basics just fine. It has a load command, and it does not have any disk access from in here. I want to be out of here. I need to, start me a virtual terminal. We shall use screen because that has been around forever and works everywhere. So let's start the simulator again. We have the simulator. Does a ton of output because the emulation environment iterates the fourth dictionary pointer chain to find out which routine resides at which address. Just a gimmick to see if I loaded my code correctly. Switch to a different screen. Let's see if we have any source code on here. Let's try this. Yes, we do. Remember, back in the old days, fourth mass storage, persistent storage access was done in blocks. A block is 1024 bytes of typical text data, 16 lines at 64 characters each, no carriage return. Each line had a fixed length of 64 spaces. And well, that's how source code got read in. There were commands to load and store blocks directly from disk. And we demonstrated last time around the capability of the real CPU together with a homegrown terminal program to store, to save and load blocks over a serial port. That's called the serial disk protocol, and that was the native way of a Novix to get any code loaded. Now 1024 bytes, doing that in a text editor gets a little fumbly. So the simulator also supports a fourth file format, which is basically, we take a look at one of these, which is basically a text file. You can load that into any editor of your choice. And load this into any editor of your choice, VI or whatever. You can edit this. These are regular lines. And the runtime environment pads this out to 64 characters per line. So please don't make them any longer. And please do not have more than 16 lines in your fourth file. We can load one of these. No, we need to start the simulator first. Dum-de-dum-de-dum, there we are. Shall we remember caps lock? We do an 8 load. And that takes a moment, and we come back with OK. And yes, the delay, the noticeable delay between hitting enter and the OK comes courtesy of my big bit bingo exercise. If we now do a words, we have something that scrolls out way too fast. Let's go back and display what we just rolled out of the screen. And that got cut off. Lovely. Do an 8. Load again, do a words. And somewhere here they have to be, I want this in hex. Words, okay, here we go. They need to be at a, there they are. My 2 words have been compiled to addresses 9A and 8A, and they are there more than once because I loaded this thing more than once. What these do was one of the problems that we're faced with, that the emulator, an emulator, chances are the timing doesn't match the original, and we shall see in a moment how badly that is the case. The emulator has a timing issue inasmuch it started feeding blocks way too quickly to the simulated CPU. The simulated CPU was not ready for any kind to accept bits, and this thing started throwing in bytes fast. So I thought, okay, fine, I just load the same functions again, again, again. Run a load command, Eversoft, repeatedly. To my great surprise, one should read source code and documentation before one embarks on these kinds of exercises, which of course I didn't. That would have made sense. Fourth remembers, or the CM fourth remembers which blocks it had loaded. Has 2 buffers. One at hex 800, the other one at hex C00. If a block is already in memory, it will not load it again. I was under the impression that I'm reloading. I was not. As a consequence, the load command didn't really load. So the serial port got never exercised. If you think about it, doing things this way makes a lot of sense, because serial ports at 9.6 kilobit are not exactly the fastest thing on the planet. And yes, we are talking 9.6 because this was late 80s and 115 wasn't really an option. So we came up with these, or I came up with these 2 caps lock again. Functions send block requests a block from the controlling terminal back in the old days, from the device that was talking to the board, but hey, we no longer have a board. It's all virtual. So let's use virtual machine terminology. You have a host, you have a guest. The Novix is the guest. The hypervisor on the real hardware is the host. What this thing does is send block requests a block, read block takes a block from disk and, well, reads the block. So what else is in here? Everything else works pretty much as it used to. Where is the test routine? Where is the test routine? Like there's self-test code for memory. I just have to find, here we go. Let's run this thing. and it does something. What else is there? Yes, it's an emulator. It's an emulator. So one thing you don't have is hardware. So the old board had all its pins on an edge connector. You could basically go out and attach TTL level hardware, 5 volts, 0 volt stuff, fairly straightforward, fairly easy to do, and start talking to it. That doesn't exactly fly these days because this is a Linux box. Well, in this case, it would fly a little bit because this is a Pi. A Pi has GPIO, so it would be possible to map some of the virtual processors, virtual bits to actual ports, and then start playing with 3.3 volt logic chips, modules, whatever floats your boat. So sorry, it's not 5 volt tolerant. You would have to do something about that. But there's one caveat. The original was clocked at close to 8 megahertz. That was as high as it went because memory chips back then, well, they topped out at that rate. You can probably get something faster right now, but 8 meg was as good as it got. The Novix executes most of its instructions in one clock cycle. Since you can piggyback more than one instruction into the same instruction word, a Novix is, there's no microcode. Every bit in a word, every command directly controls something in the CPU. There's no interpretive layer, whatever in there. A return instruction has its own bit. Therefore, a return can be piggybacked on other instructions. But for a rule of thumb, a Novix can execute 8 million instructions per second, unless one of the only instructions, or there are instructions which require an operand, which would be a memory address. These take 2 instructions. So if we assume a mix of, say, just give me a number, 80-20, or yeah, 75-25, let's say 3/4 of all your instructions are single word instructions, then you still top out at 6 million instructions per second. This is a Pi 2B, 900 megahertz. So let's find out how many instructions per second this thing does. If we do a control closing brackets, the simulator has an instruction counter. Each instruction counts it 1 up. If you hit this thing just right, then it tells you how many instructions it did per second over the last measurement interval. This right now is 1.3 million instructions per second. Do that again, this number will drift a little bit, but it's going to be in the same ballpark. If you hit this too often, your precision tanks, but it will get back. So you're talking 1.3 million instructions per second. Spoiler alert. This is 900 megahertz. And remember, we are talking 80s tech. If we run a top, we can see a couple of interesting things. Like for starters, I've been talking about this thing, or I've been running this thing now for 10 minutes. The emulator, remember, there's little supporting hardware on there. And oh, by the way, it also doesn't do interrupts. The CPU interface is bit banged. The serial interface to this thing is bit banged. That means this thing pulls the whole time. There's no pause, there's no idle state in this emulator, just as there is no idle state in the real CPU. This thing is always doing something. As a consequence, it will busy out one CPU. The only reason that we are getting these 1.3 million instructions out of this emulator is it has its own CPU. So if we look up here, our CPU utilization is 25% in user space, very little in system. We are 74% idle. If I were to crank up a second one of these, which we can do, not a problem, we would be looking at 50% CPU. So if you get any ideas to do this on something with not so hip temperature management, let's find out how we are doing. We're looking at 42 degrees centigrade. Before I started this talk, I checked I was running at 39. This is a Pi 2. A Pi 2 has a decent temperature budget. If you do that on a 4 or a 5, expect your fan to never go off again. What else is there? What else? Oh yeah, we need to talk firmware. The firmware of this thing is the original, it's the one from the fourth Systeme Angelica Flash, the German distributor of this board. There's also an original firmware that came with the simulator. They don't differ much. There is the different blurb for the copyright, and there was one instructions which changed the number for a times, how often times was executed. That came courtesy of an off by one bug that got fixed in between. But firmware, you can of course compile and load your own because hey, it's a simulator, it's easy. Firmware comes in two flavors. You can do either bin files, a binary, just a binary blob of length of 8K, because that was the original length of the EPROMs. Surprise, most of them is empty. This is very memory efficient. The other one are hex files. These hex files are a leftover of the EEPROM burner that I constructed from scratch for this thing because I didn't want to exactly entrust irreplaceable memory chips or firmware chips to some programmer device out of China, which even when it's more expensive still comes with questionable documentation and who knows what kind of drivers. So I built my own. These hex files, we take a look at them. They look very familiar because they are Motorola S records. It's pretty much what programmers, it's one of the formats these programmers understand. The other claim to fame of these things is that they are really easy to read, and a read and write mechanism for them is implementable without too much code. So, and this is pretty much as good as it gets. As far as sample code goes, the fourth files here, if we take a look at them, most of them are tiny. Number 6 is a little bit chunkier. This thing here demonstrates some of the issues that I've had with the simulator. I did not have, I needed a function that sets memory to test the disk I/O interface. And I had some issues with the simulator stack, and I wasn't quite sure how my stack looked like. Could look at it from the outside, but I wasn't quite sure if stack access the stuff that I expected it to access on the stack. So there is some stack manipulation here that would not make any sense for a real system. But if you would like to find out where on the stack something ends up as in comparison to real memory, if you maybe have an off by one in there or something like that, it helps if you can write certain patterns onto the stack and then look at them in the outside monitor to see if they ended up at the right address. Again, lots of debugging. There was time spent on this. It's not yet available because it's a little bit rough on the edges. And I would like to add a merge Ulrich's code, which does I/O way faster than mine, into this, so that you have a choice of what you would like to do. Let's see if we can at least make read block work on this thing. It requires a block and an address. Do we have any blocks here? Are there any BLK files? Yeah, there are BLK files. I have, for instance, one that's called BLK. This thing here, ooh, that looks like binary gobbledygook. It doesn't matter. Let's try it anyway. Our simulator is still running. We could state, what was the calling convention? Block number first. And we need an address. Are we in hex? We better be in hex. I don't want to overwrite my code, my firmware. Let's say we want to read block number 0 to address. This thing is 32 kilobytes, so let's load it at the 16K boundary BLK. And it reads, and the suspense is killing me. And I think I just hung this thing. Oops. That is not a problem. We just boot this again. Quit out.
It's that.
Say go. Say go. Caps lock. Do a no. Hex. Do a 4000 read block. Why not? Oh, because I forgot to load that stuff. Take a look at this block again. So sends the block, puts 1023 up there, wants the number of the block first, then the address. Number of the block first and then the address. Let's do it the wrong way around. Yeah, now I really overwrote something. But we can stop this thing and now look at memory. Help gives help. We want to display memory. We want to display this, no, not uppercase, lowercase. Display this from address 0 for 100. What am I missing? Oh, I forgot to specify which memory. And there is my memory, and apparently I did not step on it. Well, okay. Future works. Anyway, this is that. Oh yeah, you can run more than one. Last but not least, let's busy out this thing. You can run more than one of these. And if we now look at top, there are two of them, and they're happily ticking, and they will happily eat your CPU. Again, on a newer system, which more intricate memory and CPU management, you probably can get to the original utilization of the original system. But don't expect any real-time performance out of this, especially if you cannot dedicate individual CPUs to the simulators. Perfect. That's that. Questions, please.
Thank you very much. Thanks, Cornelius. Are there any questions? Everyone's overwhelmed.
I get that a lot.
All
Yeah, I
right.
know. This is a little bit the sip from the fire hose. Just wait until we walk through the code.
Yeah. Anyway, well, we can do a scheduled break. Yeah, so that is what our current schedule says. We will have a short break so everyone can sip coffee or tea or whatever your favorite beverage is. And my proposal is we will meet in 15 minutes. Is that okay?
Perfect.
Yeah,
Okay.
which is half past whatever your hour is. Okay.
Can you put a link to the emulator somewhere? I always want to play with the NC4000 CPU.
NC4000. The 2000 is the Harris that you're thinking about.
Okay, yeah, the Novix chip.
Yeah, yeah, I can put this, but keep in mind, this is work in progress.
Yeah.
This is work in progress. And so there is this thing is likely to change without much ado. Might put this on GitHub or wherever we put this stuff. I can probably put something. Yeah, I shoved this onto my website. Give me a second.
I had some conversations with Dr. Ting, and I asked him about the Novix, and he had several boards unused, and he would sell me one for $150. And being foolish at the time when I had money, I didn't buy one. And
Ouch.
yeah, and now I regretted it a bunch because
I
it
bet.
sounds like an interesting device.
Yes, it is.
Hey, I tell you what, as far as Linux versions go, the majority in here, are you running a 32 or 64-bit Linux?
64-bit Linux.
64.
Okay. In that case, we'll do this different. I have another version, but on Ubuntu. Ubuntu LTS on Intel, which I'm currently getting to the point that it no longer complains. The compiler complains quite a bit when running on a newer Linux. This box has been on purpose not gotten anything but security patches. Because it's an outside-facing device. So if you had a VPN configuration, you could actually get in here and play with this thing. B, it's a 32-bitter and it's a little bit older.
Okay. Well-
If you take the code and put it onto a modern OS, then it's not going to compile. I have one that compiles, but it throws away too many warnings for my taste. So the way this is going to work is I can publish this one with the caveat that it will not build on a newer OS, but you could look at it. Or if you give me a couple days, then I can put a newer one on there and shove this into Facebook and the usual forums.
Okay.
Your pick.
Well, I have, besides my multitude of computers all running Linux, I have some Pi 2s, Pi 3s, and Pi 4s that are just sitting in a box being unused.
There you go.
So
There you go.
I could load it up on, like a Pi 2 or a Pi 3.
That would
And
work.
it wouldn't hurt my feelings at all if it's dedicated for that purpose.
Yeah. Again, be careful if you put this on something that does not have enough anything with a temperature budget challenge might take damage.
My Pi 4s have metal heat sinks,
Oh, good.
connect to all the major chips and dual fans. And I'm on a hot day, it goes up to 39 degrees C.
Okay.
It
Good.
really cools down the device.
Good. In that case, let me bundle this up.
Yeah, and if you put it in the fourth Facebook page, then when
Yeah,
you're
that
then,
I'll drop
then
this
I'll
into
be
the
able to
chat
catch
here.
it.
Yeah. I'm going to get this over there and SCP-28. I want to copy this. No, wait, there's something missing. Click. Perfect. Okay, we leave this. No, wait, did I leave these running? Did I leave them running or did I stop them? Okay, he's down. He is not.
By the way, I like CM4s.
Yes, this thing is nice, easy, straightforward, and whatnot.
Yeah, I like it better than 2012 or all the other 83 or whatever. And for years and years, I used to use Pygmy Force, which
Okay.
is based on CM Force, and I love it.
I bet.
It's so tiny. I used to create applications for work to talk to file servers and get it. I used to be a network administrator. So I write my own little applications to talk to the servers and gather data as to what they're doing, and what's going on. And from home, I would dial in, run my application, go have some coffee. I come back, all this data is gathered for me as to what everybody's doing, and it
Yeah.
saved me a lot of time.
So, gonna shove this onto the Raspberry Pi web server here in a moment.
Usually I run Mint on my machines.
Uh-huh.
I have one with LMDE, which is a Debian version of Mint. And this PC I'm on right now is definitely way out there. It's an experimental version that I'm running. Well, not experimental to them, experimental to me. OpenSUSE Micro OS,
Okay.
immutable, rolling upgrade. It's really, really nice stuff. And so far, man, I'm happy with it. And I might start putting it on more machines.
Good idea. Okay, there's even the original in there. Good. I'm going to put this out there again with the stipulation. Be careful. This is not production ready.
Yeah. I'm used to that. You know, the little bit of programming I dabble, definitely it's not production ready either. Yeah.
If you change anything, if you find anything, change anything, please let me know that I can stick it in here.
Okay.
So,
And Pablo, I'm not an expert, but I dabble a little bit with Windows programming and a little bit with Linux programming. And I was blown away by the difference. Linux was so much cleaner and easier to deal
no
with.
kidding.
I mean, it was like night and day how much simpler Linux would be to program it. But
Yep.
you need to find a real Linux programmer, not an amateur by night type of guy.
So here we have that. Where is this thing? Ah, here we go.
And in case things don't work out, remember, computers are evil.
Oh, are they ever? So now just take the right permissions away. Star dot click ls-lsa. So this looks reasonable. Now let's see if I can get there. I think I'm going to start the screen sharing really quick for just one more moment. Alt S. I want to share this.
Now,
Sag share. So now we go to worldwide. No, too much
let
time.
me ask you a question.
Yeah.
You're running on a oh, now I forget the name. On a 2, Raspberry 2.
Yeah.
Will this software run on a Raspberry 4?
Absolutely. This
Okay.
does not have any.
This is way faster and got way more RAM, and I can put a decent Linux on it, and it's pretty comfortable with it.
It uses very basic IO read write select for console input. So the console, like the real thing, your input is being pulled, but we don't do that during every CPU instructions. But I think only every 24,000 or so CPU instruction does this thing check if there's any input available. So let's see if that gets me somewhere. Ah, there we go. Okay, here we go. I'm going to drop this into the chat right now. Emulator work in progress is here. Click, click, Control V. There you go.
Do you have your own web server available in public?
You're looking at it.
Oh, okay. Hmm.
So if you go here, this folder is not visible from the main page.
Ah,
That's why I dropped that thing in there, because otherwise, if this gets out into the wild, then the questions will never stop. And that's why I put this here.
the NSA forced you to make it secret, right?
Naja, it's like